All right, so now we're going to talk about the atomic structure of atoms and the periodic table. So let's go ahead and get started. So an overview of today's discussion will entail discussion of atomic theory, talk about the atomic number, talk briefly about isotopes. We'll discuss features of the periodic table, some characteristics of those different groups found in that periodic table, the actual structure of atoms, something called the electron configurations, which basically discusses the arrangement of electrons of an atom, and then we'll briefly discuss electron dot symbols. So to begin with the atomic theory, the initial questions about the periodic table and things of that nature can be traced back to Greek philosophers. Initially, Aristotle believed that matter could be divided indefinitely. There were others that argued that there was actually a limit. And it was during those times that the original adoption of this title, atom, was applied. And so the smallest particle that an element can be divided into and still be identified is considered an atom, which stems from the Greek word atomos, which means indivisible. Now, within the four assumptions of the atomic theory, there are four things that we are going to use as kind of our precepts. They are that all matter is composed of atoms. The atoms of a given element differ from the atoms of all other elements. Chemical compounds consist of atoms combined in specified ratios. Only whole atoms can actually combine, so you don't get partial atom fractions. And then lastly, chemical reactions change only the way atoms are combined in compounds. And that kind of precedes the idea of saying that, you don't have a chemical reaction that produces a novel compound that has a novel set of elements that didn't exist before. So, the basic understanding of an atom is that it's made of these small, tiny things called subatomic particles. Subatomic particles are the protons, neutrons, and electrons. And those are important particles that you'll want to know when you start learning about atoms. There is the proton, which carries a positive electric charge. It might be denoted by a positive +1. Then you have your neutrons, which are similar fashion in terms of mass, but they carry a neutral charge, and usually they're represented with a 0. And then you have your electrons, which are negative in nature, and they generally carry a -1 charge. Now, the electrons are so much lighter than protons and neutrons that in general, when people calculate their mass, it's usually ignored. Now, a comparison of these subatomic particles, going back to kind of restate what I was mentioning before in the previous slide. If you look at the proton, it represents that +1 charge, and this is roughly its mass of 1.672622 times 10 to the -24. So you can kind of get an understanding and qualify that it's pretty small, and it makes sense because it's a subatomic particle. Then you have your neutrons, which are comparable, and they have a charge of 0. And then lastly, you have your electron, which is a few orders smaller and carries a negative charge. And they usually represent the mass of atoms and subatomic particles using a relative mass scale. Basically, you count the number of protons, and you count that number of neutrons, and you add them up, and you kind of go from there. Now, the basis for the scale is an atom of carbon that contains 6 protons and 6 neutrons. This carbon atom is assigned a mass of exactly 12 atomic mass units, or Daltons. Now, respectively, when you think of the atom is this cyclic structure, and in the centralized portion of it is a nucleus. Now, in the nucleus, there are these subatomic particles called the protons and neutrons, which we just mentioned in the previous slide. Now, what needs to be known as a relative comparison is that, for the most part, the nucleus only represents a small portion of the entire atom. And in the image denoted here, you'll notice that they represented kind of a baseball stadium. And as far as relative size is concerned, this area of the actual stadium could be just the space that's occupied by something called the electrons. Now, if we were to focus on just the nucleus of an atom, it actually would be the size of putting a pea in the center of the baseball stadium, and that would be used to contain the protons and the neutrons. And so they're packed really, really tightly inside of that nucleus. And emanating and just kind of moving around in the area are the, what you would call sea of electrons, or the electron subatomic particles. Now, as far as interactions are concerned, one thing you need to note is that opposites tend to repel each other. This means that in general, electrons, these particles do not prefer to be near each other, and they do everything they can to move away from each other. Same can be stated about the protons within realm. Interestingly enough, this is a situation where opposites do indeed attract. When you have your protons and you have your electrons, because the protons exert a positive force and your electrons exert a negative force, they tend to pull each other together. And this strong force is called the nuclear strong force. Now, some historic origins of atomic theory, well, you know, the initial adoption of the atomic theory was proposed by John Dalton, and this occurred in 1808. Kind of briefly summating this, J.J. Thomson then determined the mass of an actual electron. We later find that Robert Millikan identified the charge on the electron as being negative. Then you have the Rutherford experiment, which allowed him to deduce the existence of the nucleus of an atom. And then the last part, which applies to this image, is that you have a scanning tunneling microscope, which makes individual atoms visible. It makes them visible, so you can actually see them. So that's kind of a brief history. You have Dalton, then you have Thomson, determining the mass, Millikan, who identifies the charge, and then you have Rutherford, who is able to identify the actual nucleus of the atom. And we're able to see it using a scanning tunneling microscope. Now, there's a number on the periodic table called the atomic number. And if you're going through the rest of this lesson, you probably want to have the benefit of having a periodic table near you. The atomic number is the number of protons in atoms of a given element. And so usually on the periodic table, there's usually like two numbers that are found with each element. And the smaller number is going to be representative of that atomic number. And you want to know that that represents the number of protons in an atom. And all atoms have a distinct number of protons. A lot of times I like to say that it's like the Social Security number for the atom. And it is used to identify the atom. Now, if we look at the mass number is something different. It's usually the larger number. In fact, almost always is the larger number, and it represents the sum of both the protons and the neutrons. And so a lot of times as an organizational practice, what I tell people to do is, hey, suppose you're trying to determine the number of neutrons of an atom. Well, you simply subtract the mass number from the atomic number to find the number of neutrons in any particular atom. Now, atoms are neutral because the number of positively charged protons and the number of negatively charged electrons are generally the same for each atom. If the number of electrons change, which you'll learn about later on, then it becomes kind of a charged species, and that's a different discussion. For the most part, when we're looking at just the basic periodic table, we're assessing them based on the premise that they are all neutral. Now, you have some kind of special elements out there. In this case, you have atoms called isotopes, and they have identical atomic numbers, but they have different mass numbers. So having a different mass number would basically suggest that they have the same number of protons, but they may have a different number of neutrons. One such example lies in that of protium, deuterium, and tritium, and they're all isotopes of hydrogen. And they're found in relative percentages when you think about hydrogen itself, and they contribute to what hydrogen is, but all of them are similar in the fact that they have one proton, but they have a variation in the number of neutrons. Now, a specific isotope is represented by showing its mass number as a superscript and its atomic number as a subscript in front of the atomic number symbol. For example, the symbol for tritium is denoted below. You have your mass number of 3, and you have your atomic number of 1. Mass numbers on the top, the larger number, and the atomic numbers on the bottom. Now, the isotopes of most elements do not have distinctive names. And so the deuterium, tritium, protium thing is kind of a exclusion, and it's not necessarily the rule for all other isotopes for elements. So mass number is given after the name of the element. The isotope used is usually denoted using some kind of number, such as like for uranium, it might be uranium-235 or U-235. Most naturally occurring elements are actually mixtures of isotopes. And that just means they have the same number of protons, but they may have a different number of neutrons. Now, one thing that we're going to be looking at when we talk about atoms is something called the atomic weight, and it represents the weighted average mass of an element's atoms. And you can essentially determine an atom's atomic weight by looking at the chemical formula and determining, how many of those atoms are available and so forth and so on. But the general definition of atomic weight is calculated as the sum of the mass of the individual isotopes for that element. So you have an element, and it has basic smaller proportions of isotopes that contribute to its total weighted average. A lot of times I try to make the analogy of if somebody looked at their final grade, it's a representation of the weighted average of their tests, quizzes, and other assignments, and each part contributes a certain percentage for the total grade. That's how atomic weight similarly, where atomic weight in this analogy is actually your grades. So on the periodic table, there are only 10 elements that have been known since the beginning of recorded history. In the late 1700s and early 1800s, as more elements were discovered, chemists began to look for similarities among elements. Dobrinner observed in 1829 that there were several triads that appeared to have similar chemical and physical properties. And it wasn't later until we got our father of the modern periodic table, who was Dmitri Mendeleev, who organized the elements by mass and into columns based on chemical behavior. Now, what's also interesting to note about Mendeleev is that he was able to kind of predict elements in the periodic table that had not even been discovered yet based on his arrangement of the periodic table. And so he is known with the early prediction of the modern periodic table that we know today. Now, on your periodic table, there's a combination of 3 things. You have your atomic number, you have your representative symbol, which usually denotes the element that it's corresponding to, and then you have your atomic mass. We've already talked about the atomic number. It represents the number of protons. In a neutral atom, it can also represent the number of electrons. That's important to note. For your atomic mass, that number is usually your larger number. You can actually use that number to extract your actual number of neutrons, because very similarly, atomic mass can be representative of the whole number version of the mass number would be the whole number version of your atomic mass. So here's the extent of the periodic table, its breakdown. We have the metals, metalloids, and nonmetals, which we kind of discussed before. And they're divided into those 3 sections, and there you can see not only the atomic numbers of each one, but also their atomic mass for each element. And you can extract the mass number, the number of protons, number of electrons, everything thereof. So now we're going to kind of look at those groups and how they're broken down. So the vertical cross sections of a periodic table, there are some that are made into main groups, And then there's some that are broken down into transition metal groups, and some broke down into inner transition metal groups. And we'll be looking at those based on their column breakdowns. But kind of going forward, you also have a zigzag region of your metalloids. And we already discussed the elements to the kind of right are your nonmetals, the ones on the left are your metals, and they're grouped by their column vertical sections, and they're grouped largely because of their similarities in reactivity and behavior. And so each grouping vertical section is going to be called your family. Now, going laterally, you have these things called periods. And so going from left to right, there are 7 periods. And so that's kind of another extension of the arrangement of the periodic table. This slide basically tells you how many elements are associated with each period, but you want to know that a period just travels laterally. And there, for the groupings, there's 2 different ways for indicating the groupings, but it's not as significant as just understanding that their behavior and reactivity is very similar. The inner transition metals aren't numbered the same way because they go through various reactions. Same thing with your transition metals. And then your main group elements can actually have more preset number designations because of their similar characteristics and reactivity. And so the graph above actually shows the relationship between the atomic radius of each element going through the periodic table. And I don't know if you're seeing the trend, but as one travels from hydrogen to lithium, the atomic radius increases, then it decreases going down to fluorine, and then jumps back up to sodium. And there is a trend associated with the behavior when you're traveling left to right and top to bottom when it comes down the periodic table. In fact, if you want to know the actual trend going from left to right on the same period, the atomic radius of an atom actually decreases, but then going down, it actually increases. So that's that. Now the